Mathematics and physics have actually developed in parallel or together for many centuries. And very often you couldn't tell whether a particular scientist was a mathematician or a physicist. One of those cases is Isaac Newton, of course, who developed and used differential calculus, developed jointly with Leibniz, of course, differential and integral calculus, to write his laws, his basic laws of mechanics. And that actually, you can think of this as the moment when the research field of applied partial differential equations was born. Ever since then, physicists have used the descriptive language of partial differential equations to describe important phenomena. Think of James Clerk Maxwell, who was mentioned by John. Think of Ludwig Boltzmann, gas dynamics. Think of Albert Einstein. Think of Erwin Schrödinger. So, I mean, for a while after Newton, again, mathematics and physics developed jointly, but then in the last century, or maybe a bit earlier than that, there was actually a split. And mathematics and the mathematics of differential equations became an important subject of its own. And really in the last century, and at the end of the last century, it had what I would call almost an explosion of results and new theories. So then actually, the theory of differential equations was also used for other fields than physics. For example, biology, for example, social sciences. And in this lecture, actually, what I want to do is I want to show you, well, I want to give you glimpses on certain classes of problems, and I should say very superficial glimpses on certain classes of problems where differential equations can be used for the benefit of science in general. And that, of course, I mean, we're mathematicians, so we always want to keep the beauty of mathematics within the game. Okay? So, I mean, this is not an exhaustive list of problems, of course, that you could think of in the field of applied partial differential equations. It just reflects what I would say is my personal choice. Okay, so don't blame me for not being exhaustive in this context. Okay, in the year 1900, I think November 1900, the German physicist Max Planck gave a very important lecture to the Prussian Academy of Sciences in Berlin, in which he discussed his new research on black body radiation. And he was actually quite appalled by his own work in some sense. He said, well, unfortunately, I couldn't get a hold of the problem without doing something terrible, without quantizing energy. And he was really, as I said, he was appalled by it, and he didn't like his own approach, but didn't find another way of doing things. So that was actually the moment that we now consider as the moment of origin of quantum mechanics, which is really a theory that has, I would say, rewritten physics of the last century completely. And then after Planck's lecture, it took some 23 years until the mathematical equation, the basic mathematical equation that describes quantum mechanics was formulated by the Austrian physicist Erwin Schrödinger. And this is really the first class of problems that I would like to discuss here. So the Schrödinger equation, as you see it here, is a partial differential equation for a typically complex valued unknown, which we refer to as the wave function psi, which depends on spatial variables, x, and on time t. And, well, if you look at the equation, what you see is, well, you see a spatial Laplacian entering, you see a time derivative on the left-hand side, and you see the imaginary unit I enter on the left-hand side. This is one of the reasons why the solution of the equation is, of course, complex valued. Well, then you have a function v external, which should model external potential forces that act, say, on the particle whose motion in a quantistic sense you are describing. And in many cases, you have to take into account nonlinear particle-particle interactions. So what you see here is a very, very generic form of the nonlinear Schrödinger equation. Now, nonlinear Schrödinger equations are very general description tools for nonlinear wave propagations in dispersive media. So for example, they can be used to describe phenomena in nonlinear optics. So think of laser beams in optical fibers, for example. Or they can be used to model quantum superfluids like Bose-Einstein condensates, and I shall talk about those in a moment. They can be used to model phenomena in plasma physics, but they can also be used in what I would call non-quantistic problems, for example, in the description of water waves and tsunamis. And eventually, they can also be used for describing superconductivity, something that I shall also talk about in a moment's time. Okay, here you have two prominent examples for nonlinear Schrödinger equations. Example one is the repulsive Schrödinger Poisson system, say, in 3 dimensions. So what you have is the Schrödinger equation for the wave function. You have an external potential, and you have here this self-consistent Coulomb term that models the repulsive Coulomb interaction of, say, electrons. Say that you're interested in describing electrons that move in a crystal semiconductor lattice. Okay? But then this potential here would be periodic on this lattice. It would sort of represent the forces that are generated by the ions that make up the lattice. Okay? The second class of problems that I want to describe is, well, the celebrated the celebrated Gross-Pitayevsky equation for Bose-Einstein condensation. So what you have here is, well, what you want to do is you want to describe the superfluid dynamics of a Bose-Einstein condensate. So first of all, what's a Bose-Einstein condensate? Well, think of it as a very dilute gas of ultra-cold bosons. And by very dilute, I mean much more dilute than the atmosphere that we live in. And by ultra-cold, I mean nano-Kelvin temperatures. Okay, and that's actually an interesting history of Bose-Einstein condensation. Actually, the first who theoretically thought about it was the Indian physicist Bose in around 1920. And after that, Einstein got a hold of his work, and Einstein understood immediately what it was, namely a phase transition in terms of temperature. Now, that was back in the 20s, and that's an interesting case. I mean, there was absolutely no way for many, many years to produce or generate a Bose-Einstein condensate in a lab. Just physicists, experimental physicists, didn't have the cooling techniques. And this happened for the first time around the change of the century. Actually, I think in 1995. So that was really so. I mean, there is about a 70-year delay between theory and experiment, which in some sense is very atypical. I mean, we mathematicians, we often tend to think in the other sequence term, right? Okay, that's the way it was. Now, the equation that models Bose-Einstein condensation, or actually what happens with the condensate once it's formed, is the Gross-Pitayevsky equation. So what you see is a cubically nonlinear Schrödinger equation, where the cubic term here models particle-particle interaction. So that is interactions of two bosons. And you have a laser trap. You have to think of that in the laboratory. The Bose-Einstein condensate is generated under the influence of a laser which confines. Otherwise, you just wouldn't see anything. It would just flow away. Okay. So think of this Vx as some quadratic confinement potential. Now, interestingly enough, a Bose-Einstein condensate can be both repulsive or attractive. And so, I mean, that changes the sign of this coefficient here. And the physicists know how to tune it in an attractive way or in a repulsive way. Now, what I want to show you here is actually pictures which were taken in a lab. I think this was probably the first successful experiment on Bose-Einstein condensation done by a group of experimental physicists in Colorado. And what you see here is the density of the condensate over momentum space. Okay, so you think of the momentum plane, and you see the density of the condensate above it. So what you see is, when temperature is sufficiently large, you see some kind of Gaussian type distribution. Okay, now when temperature becomes smaller, you sort of approach the phase transition, and the Gaussian distribution gets more and more peaked, and eventually, theoretically at least, at 0 temperature, it should become a delta distribution, which basically means that all the particles in the condensate have to be in the same state. That is in the quantum mechanical ground state. Okay, what are the basic mathematical questions that we try to answer in the context of the nonlinear Schrödinger equation? Well, of course, we want to know whether there is existence of solutions, whether there is existence of local or global solutions. If the solution turns out for some reason not to be global, which may very well happen in both attractive and repulsive cases, then we want to know what happens how does so-called blow-up occur. Now keep in mind, by the Schrödinger equation, the total mass, which is just the L2 norm squared of the wave function, is conserved in time. Okay, so what does blow-up mean? Well, blow-up means basically when this mass density concentrates, or in other terms, when the kinetic energy term becomes infinite when you approach a certain time. So that is an important mathematical question. Other questions refer to soliton dynamics, of course, and then there is asymptotic problems for asymptotic questions for long time behavior, like scattering of solutions and other questions connected to long time asymptotics. Now, it is, of course, an important question to model the condensate after blow-up time of the Gross-Bitaevsky equation. I mean, what does it mean in terms of physics, blow-up? It's very hard to describe. I mean, you can't really describe it in direct terms. Mathematically, what you have to do is you have to take other physical effects into account which mediate the blow-up. And the other physical effect that you have to take into account here is three-body recombination, which gives, in mathematical terms, can be modeled by a dissipative quintic nonlinearity. Why do I say dissipative? Well, here you have minus I, and here you also have I, so when you just ignore the other terms, you cancel I, you end up with a dissipation term, assuming that sigma is positive, of course. Okay, so here you have a very interesting, mathematically very interesting case of interaction of dispersion, cubic nonlinearity, which may be attractive, and quintic nonlinearity, which is dissipative. And then here, for this case, I can tell you that in the end, the dissipation wins. But what is the mathematical issue here? Well, mathematical issues actually are that the quintic nonlinearity is energy critical. That's a mathematical problem. And of course, you lose Hamiltonian structure. Okay, so there's no more conservation laws that you can use to do your analysis. Now, still you need to get uniform bounds. Well, essentially, when you go through the analysis of Schrödinger equations, Schrödinger type equations, you need bounds on the kinetic energy, and you need certain LP bounds on the solution itself, okay, for a certain P. Okay? And those actually turns out that they can be obtained by using a priori estimates on suitable energy type functionals. Okay? So basically, the idea of energies, looking at them, really remains upright, but of course, you have to modify many things. Okay, when Planck gave his lecture in the year 1900, he also said, well, he said many important things, but one extremely important statement was that classical mechanics, that is classical Newtonian mechanics, is the limit as h bar tends to 0 of quantum mechanics. Well, that's a weird statement, right? Because h bar is a number to which physical units are attached. Okay, so how can it converge to 0? Of course, we mathematicians know how to deal with that, and that is through scaling. So when you scale the problem, or when you scale the Schrödinger equation appropriately, what you find is that an important parameter an important dimensionless parameter turns up, and that parameter is, of course, the macroscopic length scale. Okay, let me call this parameter epsilon, and well, then when you do the scaling appropriately, you realize that this parameter epsilon turns up in front of the time derivative on the left-hand side, and its square turns up in front of the spatial Laplacian on the right-hand side. And here, for the sake of simplicity, I have neglected all the other terms. Okay? So think of this extremely trivial linear constant coefficient problem, and let me assume that I excite the problem at time t equals 0 through a plane wave with a huge wave number. Okay? So then you can, of course, actually you can ask your favorite first-year undergraduate student to compute the solution explicitly for you. He will say, Fourier, right? And that is the solution that comes out to this initial value problem. And what you realize is that order epsilon oscillations, I mean those that you put in at time t equals 0, they are propagated through the equation in space and time. Okay? So, I mean, this is, of course, a very simple problem that you can solve explicitly, but when you think of adding potentials or nonlinearities, then, of course, the explicit computation goes down the drain, and you have to think of something more innovative than that. Okay? Now, this is a highly non-trivial multiscale problem, even in the case where the nonlinearity is not present. In particular, when you think of what we call slow-fast coupling, or homogenization in slow-fast coupling, which would be that the potential is a sum of a slowly moving potential and a fast-moving periodic. And you have absolutely non-trivial questions to answer mathematically. Well, clearly first of all, maybe the applications. Where and how can you apply this? Well, first of all, when you do electron dynamics, say in semiconductor crystals, okay? Or when you do Bose-Einstein condensates in so-called optical lattices. As I said, when they do Bose-Einstein condensates in the lab, they expose it to the effect of a laser beam. Now, they can also do optical lattices where they have a multitude of lasers acting on the condensate, and those lasers may very well be of very different frequencies. Okay, and this is the way to generate an optical lattice, which then is reflected through a periodic potential, through a highly oscillatory periodic potential in the equation. Now, what are the mathematical ways of analyzing this? Well, we have a very strong tool which is called Wigner measures. We have other tools, double-scale convergence, homogenization techniques through double-scale convergence methods. We have space adiabatic perturbation theories, and we have two-scale WKB expansions. Okay. Now, how far do we get with all those beautiful mathematical techniques? Well, we get somewhere, but not to the end of it, particularly in the nonlinear case. So far, we only have short-time results. And by short time, I mean before the occurrence of so-called caustic sets, which are singularities, which are sets of singularities in space-time of an associated Hamilton-Jacobi equation. If you add multiscale potentials, we can treat only weak nonlinearities. Okay, that is nonlinearities which are of the order of the perturbation parameter epsilon. So you see, we still have a long, long way to go to understand those analytical issues. Now, in my view of the world, whenever there is a serious analytical issue, it will also be reflected by a serious numerical issue once you go down the track of simulating the problem. Now, when you simulate, well, when you discretize, first of all, Schrödinger type equations, you might do what everybody does for the first time when he starts on the problem, use finite difference discretizations. Well, actually, it turns out that those are very, very bad for semi-classical Schrödinger equations. You need very small mesh sizes, which are very small compared to the order of the perturbation parameter. That means when you use finite difference methods for semi-classical Schrödinger equations, you must be prepared to resolve all the oscillations in the solution accurately. Now, when you think of 3D, when you think of a time-dependent problem, of course, in 3D, when you think of a small semi-classical parameter, say epsilon equal 10 to the minus 3, well, you can sort of figure out by yourself how many grid points you would need in order to compute a reliable and accurate solutions. And actually, it turns out that the chemical literature is really full of those computations, and usually the way it's done is just compute once and accept whatever you get as a solution. This is, of course, very, very risky, because in these computations, which bring you sort of to the borderline of what you can actually compute within reasonable time, you just don't have any space, any computational space, to do another refined computation and to double check. So in the end, sometimes what you see is a lot of waves which oscillate, but you don't really know what they are. Okay, now there is better techniques. Time-splitting schemes generally are much better behaved. They can actually also be extended to the case of periodic potentials. And there, the basic idea is that you take your nonlinear Schrödinger equation and you split the computation or the time integration into two steps. In the first step, you just solve this linear Schrödinger equation with the periodic fast potential in it. And of course, the trick will be how you do that. The second splitting step would just be solve this ODE, ordinary differential equation. Okay, that's absurd. I mean, that's absolutely trivial. The problem is how you do this. And there is actually a very nice method which is based on a functional analytic trick, which is called Bloch decomposition in this context. And you have to think of Bloch decomposition as a sort of as a fancy name for a clever way of looking at the spectral decomposition of this operator on the right-hand side here. Just to show you some, example. Well, I mean, what do you have to do for the Bloch decomposition? You have to solve an eigenvalue problem. So, I mean, the question has sort of been reduced to computing as many as you can eigenvalues of the periodic Hamiltonian, but on a bounded domain using periodic boundary conditions. Okay, that's sort of I mean, in a nutshell, that's the computational trick. So what you see here is a computation of a 3D lattice Bose-Einstein condensate, where at time t equals 0, we just start with a Thomas Fermi ground state, and then we just let the system evolve. And here you see the evolution after one time unit in the repulsive case. So basically what you see is that the initial wave has spread out wider. And here you see the corresponding computation in the attractive case. So you see this peaking of the solution occur. So it means we can now solve numerically, rather effectively, very, very complicated nonlinear Schrödinger problems, even in the highly semi-classical oscillatory regime. Okay, free boundary problems. What are free boundary problems? Well, basically, when you solve a PDE, you have a domain and you're looking for a solution. In free boundary problems, life is more complicated. That is, you solve a partial differential equation, but in an a priori unknown domain. So you want a solution plus geometry. Okay? And of course, in order to get the geometry, or the free boundary, you need additional conditions. So basically what you need is an extra boundary condition on the unknown part of the boundary. So for example, here in this case, you want to solve Laplace u equal 1, and the additional side conditions are u equals 0 and gradient u equals 0 on the rest of the domain. And you're looking for the solution and this free boundary here. Now, where can you use free boundary problems? Well, they are very suitable for modeling a wide range of physical phenomena, like in superconductivity, in solidification theory. They are even used in mathematical finance. If you think of price formation, an issue that I might still have time to speak about it at the end of the lecture, or in option pricing. Well, then in mathematical biology, like tumor growth is is typically modeled as a One way of modeling tumor growth is as a free boundary problem. And in chemistry, of course, a chemical vapor deposition, for example. Now, what I want to show you now is a movie, if I get it. Okay. Oops. Okay, so what you see here is something that looks like magic. You see this magnet which levitates. Let me try whether I can show it to you again. Okay, which levitates over this disk. And this disk is made of a very special material. It's a so-called superconductor. And what you see here is just the well-known Meissner effect at work. Certain materials, superconductors, what they do is they expel, after phase transition, all magnetic fields, and instead of those magnetic fields, they generate electrical current. And the generation of current happens seemingly without resistance, and that is why those materials are called superconductors. And again, what you're facing here is a phase transition phenomenon. Now, where are those superconductors used? Well, they are used, for example, in certain maglev trains. They are used in wheel applications for energy storage, like what you find as in very new technology in certain cars, which use brake energy recuperation techniques. So when you look inside a superconductor, what you really see is you see a lot of vortices. And I shall tell you in a moment what I mean by vortices. And actually, in physical terms, each of these vortices carries a single flux quantum of magnetic flux. Okay. And actually, what happens is, as the material enters into the mixed mode, by mixed mode I mean half normal state, half superconducting state, then vortices penetrate into the superconductor. And the number of those vortices is typically very, very large. And when I say this, you can already smell what I'm after mathematically. I'm after homogenization. Now, there is a mean field model for superconductivity, which was actually pioneered by the physicists Ginzburg and Landau. And what they did is they wrote an energy type functional which acts on a quantum mechanical order parameter psi, which in some sense you can look at it as some kind of wave function, and the magnetic vector potential. Now, by a vortex, what I mean now is a node that is a zero of the quantum mechanical order parameter. And as I said, individual vortices are then averaged into a vortex density. And what we really want to study is the penetration of the material with the vortex density. Okay. And of course, once we do this, we will have to look at properties of the vorticity region, such as regularity, geometry, and so on. Now, what you see here in this movie is how those vortices penetrate into the superconductor. And you see that happens in a very, very wild way. Okay? And actually, people speak of a mesoscopic dendritic vortex instability. Okay, so you see mathematics. I mean, there's all kinds of very, very difficult problems involved. Free boundaries, of course. There's fractal geometries involved. And there is very, very big regularity problems. Now, when you've done the homogenization, okay, by averaging those vortex densities, what actually happens is that you find a free boundary problem, which is represented by this nonlinear elliptic equation here, free boundary problem, which is posed in an a priori unknown domain, of course. And there is big mathematical problems here, like optimal regularity, classification of what free boundary people call global solutions. And of course, as always in free boundary problem, all the theory passes through one overriding mathematical question, and that is, how regular is the free boundary itself? Once you know the regularity of the free boundary, you can conclude on the regularity of the solution. Okay, so there's a lot of actual geometry involved in those problems. Okay, reaction diffusion systems. Where are they used? Well, a typical case of a reaction diffusion system, typical cases occur in population dynamics. Think of predator-prey systems. So basically what you have is a certain number of predators. You have a certain population of predators and you have a certain population of prey. And for their own good, for the mutual good, they have to keep a certain equilibrium, right? Because when you think that in the case you have too many predators, they eat up all the prey and then there's nothing left for them to eat and they will die. On the other hand, if you have too many prey species, then the number of predators will grow in turn. They will again eat up all the, they might eat up all the prey and then they will die. Okay, so there is always a question of how do those populations equilibrate. Well, another application of reaction diffusion system is, of course, the well-known problem of pattern formation in animal skins. Okay, so I mean, how do those patterns form on the body of the giraffe? How do those patterns form on the body of the crocodile? And again, this can be modeled by reaction diffusion systems and analyzed using ideas, very, very beautiful ideas of the English mathematician Turing. Now, what are reaction diffusion systems mathematically? So think of a vector U of, say, densities, maybe density of predator and density of prey. Then you have a diffusion term on the left-hand side, or on the right-hand side, sorry, which of course tries to equilibrate everything. Okay, but I mean, though, the total equilibration process in general is disturbed by instantaneous reactions. And those reactions are represented by this nonlinear function of the density itself. Now, then you might think of a bounded domain, you might think of imposing boundary conditions, or you might think of the associated whole space problem, and then you can start to do your mathematics. Now, what's one of the main mathematical questions? Well, as I said, we are interested in equilibration problems, so we are interested in what happens with the populations in the long run, or in the question how the pattern forms on the animal skin. Again, this is a problem of a large time asymptotic state. So when you think of these, well, when you think of a system of equations like this, then of course the critical points are those where the reaction rate degenerates. Then instantaneously you lose information on possible asymptotic states. Now, I mean, those points, or manifolds actually, they have sort of to be compensated by the conservation laws that are associated to the diffusion process. Okay, so there has to be sort of an equilibrium of both. Now, how do we proceed in terms of mathematics? Well, there is a very, very interesting, beautiful approach to the long-term behavior of reaction diffusion systems, and that is using an idea that was pioneered by Ludwig Boltzmann in gas kinetics, that is entropies. So basically what we want to do is we want to exploit an entropy, or a Lyapunov type functional, which dissipates monotonically in time. Well, when I say we want to exploit, first of all, we want to find it for the system of reaction diffusion equations that we have at hand. And then we want to exploit it. Now, this clearly requires the conservation laws, which are associated to the diffusion processes, to identify an equilibrium state from the set of entropy minimizers. Okay. Now, then what we need to do is we need to go into functional inequalities, and we want to establish a quantitative entropy dissipation inequality. So we want to relate the entropy to its dissipation. And then if we can do this, we will be able to prove convergence in entropy to an entropy minimizing state as time converges to infinity. Now, once you have convergence in entropy, you can use classical inequalities from information science, well, originating from information science, so-called Čížák-Kullback-Pinsker type inequalities, which relate the entropy, or the convergence in entropy, to the convergence in, say, the L1 norm or in another classical norm. Now, interestingly enough, this very often yield, well, it should yield explicitly computable rates, which in some cases may even be optimal. And it may even give optimal constants of convergence. And the interesting thing is, mathematically, I mean, if you think of old theories, classical theories of reaction diffusion systems, they were based on linearization techniques, small perturbations and linearization. Now, this doesn't do anything like that. Okay? Entropy techniques basically are global. They do not use linearizations. Just to show you an example of a reaction diffusion system that we were interested in, what you see here is the very, very classical model for current flow in semiconductor devices. So you have a population of electrons, negatively charged. You have a population of positively charged particles, which are called holes. And both of them diffuse and are transported through some internal or external fields. Okay. Now, there is also another mechanism that generates or destroys electron-hole pairs, which is called entropy, which is called recombination generation mechanism. So a typical model for recombination generation is something which looks like this. And when you look for the degeneracy, so you have to check where is this rate r equal to 0, and what you get is a one-dimensional manifold in MP space. So you need one conservation law to compensate for it. And of course, this one compensation law comes about when you subtract those two equations and integrate. Okay, so that's more or less the idea of it. Okay, now here, let me change subject. Let me go into chemotaxis. What is chemotaxis? Well, chemotaxis is the motion of biological cells oriented up the gradient of a chemical. And that chemical may be external, or it may be produced by the bacteria or by the cells themselves. Now here what you see is the classical model for the self-produced chemical, which is the so-called Keller-Segal model. So you have a density of bacteria or biological cells, and you have a concentration of the chemical C. What happens is you have diffusion of the cells, you have drift of the cells up the gradient of the chemical concentration, and then this equation here represents the production of the chemical through the cells. Okay. Now, now in 2 dimensions, there is a very, very beautiful mathematical theorem published in a paper recently, actually not so recently anymore, by Adrien Blanchet, Jean Dolbeau, and Benoît Pertam. And it's a very sharp theorem. It's beautiful. So it says, if you have a certain bound of the initial density of the bacteria, okay, and when you compute the total mass or the total number of bacteria at time t equals 0, then there is 2 cases. Well, 3 cases, but let me speak of 2. There's 2 cases. When the mass is sufficiently small and the constant is 8 pi, then you have global existence of solutions. When the mass is sufficiently large, and that is larger than 8 pi, then you have blow up in finite time. And what do I mean by blow up in finite time? I mean that you will get concentrations in the density n. Well, there's of course the question what happens at m when the mass is equal to 8 pi, but let's forget about that for a moment. So I mean, that's a very, very beautiful theorem. It's as sharp as it can be. It's in 2D, which is a biologically interesting case. Think of a Petri dish or something. The mathematics of it is based on a very beautiful functional inequality. That is the Hardy-Littlewood-Sobolev inequality. But it has just one defect. It's biologically useless. Okay, so if you talk to biologists, they will tell you, well, beautiful, where can I put my model parameters? And the answer is nowhere. Okay, you have absolutely no freedom in doing things here. So how can you midgetate that? Well, first step of midgetation is that typically motion of biological cells occurs within some kind of medium. For example, fluid. Okay, so what you see here is the distribution of, or the evolution of the distribution of certain bacteria which like oxygen within a drop of water. So this is the drop of water. So here you see the bacteria here, the top picture is the short-term evolution, so what happens in few seconds time scale, and what you see here is the long-term picture. Okay, so what you see in the short-term picture is that there's two kinds of bacteria. I mean, there is those that make it up the drop and they can breathe, and there is those that are left at the bottom. Okay, now this is short-term. Now you see in the long-term you have those fluid dynamically well-known instabilities, and some of the instabilities even manage to resurrect some of the bottom bacteria and make them move upwards towards the oxygen. And actually I should say that this is an experiment that was done in my home university in Cambridge by Ray Goldstein, and he was kind enough to let us have the movie. Now what's the mathematics of it? Well, first of all, you have to couple the motion of the bacteria with the motion of the fluid. So your unknowns now are the bacteria density n, the oxygen concentration c, you have the fluid or the water velocity, and then of course you have the water pressure, and let me assume that the fluid density is constant. Okay, so let me disregard incompressibility effects here. Now then when you write the model for it, it's actually pretty simple to write the model. What you find is the following. You see the bacteria with density n diffuse with a constant diffusivity. They are subject to fluid convection, and they react towards oxygen. So that is, they are directed up. I mean, their motion is directed up the gradient of the oxygen concentration. So this fully accounts for the N equation. Yeah, and then here you have a chemical, a chemotactic sensitivity term built into the system. Now, there is one issue here. Of course, I only consider pure transport phenomena here, okay? So I neglect the birth and death processes of the bacteria. They would enter as a reaction term here. Now, moreover, the oxygen concentration of C. So you see that it's, first of all, it's convected through the fluid. Then you see it's diffused with, say, a constant diffusivity. And then, of course, oxygen is eaten up by the bacteria. So this is what this term here should account for. OK, then I need to model the fluid, and I need to model the bacteria-fluid interaction. And what you see here is the classical Navier-Stokes equation in the incompressible case. So here you have fluid convection. Here you have the pressure, diffusion. And this term is the force through gravity which the bacteria enact on the fluid. Okay, and that's the interaction that here takes place. Now, this is a complicated problem, right? I mean, I've shown you that even for the pure 2D chemotaxis problem, without the fluid, quite a lot of mathematical machinery and mathematical technology was really necessary. So here it's, of course, going to be worse. And let me just give you a short glimpse on what we can do. Well, first of all, there is really, I mean, from a modeling point of view, there is really no need to consider the full Navier-Stokes equations because the motion is going to be very slow. So we just drop the nonlinear term in Navier-Stokes and use the Stokes equations instead. Well, of course, we need to set the geometry, say either a bounded domain if we want to be biologically relevant, or if we want to do interesting mathematics, the whole space. You need boundary conditions. I'm not going to comment on that. And then, of course, there is questions, mathematical questions that occur. And the question is, in analogy to the classical Keller-Siegel model, do bacteria densities concentrate to singular measures in finite time? Or does fluid convection and fluid pressure levitate that problem? Okay. Can you prove global boundedness of solutions? And actually, we can do some things. As always, we can, or as in most of the interesting problems, we cannot do everything. We can prove local existence, of course. We can prove global existence for small initial oxygen concentrations. The technique is again entropy related. We consider a certain energy entropy type functional that we play with. And there's other things that we can do. We can prove under certain assumptions on the parameters. We can prove global existence without smallness assumptions. Or another way of going about it is to replacing the linear diffusion for the cells by an appropriate nonlinear diffusion term. So that is by solving instead of a porous medium type, by using a porous medium type modeling for the biological cells. Is this reasonable? I don't know, and I haven't found a biologist yet to tell me. Okay, numerical computations for this problem are really very, very involved. Keep in mind, you solve a fluid chemotaxis coupled problem, so you sort of have to find a way of mitigating discretizations. Discretization that is good for convection diffusion and discretization that is good for the fluid problem, and you sort of have to combine them appropriately. And interestingly enough, it turns out that what we can compute is those plumes that I have shown you initially in the movie of the drop of water. And it turns out that those plumes really become stationary. Okay, so here what we do is we compute a stationary solution which carries an inherent two-phase fluid interaction instability in it. How long do I have, Maurizio? Okay, very good. So finally, let me say a few words about the applications of PDE to social sciences. Yesterday we have heard about, in Iva's lecture, we have heard about contracts. I want to consider sort of related type problems here, and the problem that I want to look at is the following. Consider the market for an economic good, or for a certain number of them. Consider that you have a fixed number of buyers and vendors. Okay. Now the question is, how does the price of the good or of the goods evolve in time? Now if you could find a model for that, you would be able to predict the price into the future, which might make your economic life a bit easier. There's a main assumption to the modeling, and the assumption is that buyers and vendors do not take every single interaction on the market in account. They sort of base their decision on an overall market outlook. Okay? And then there may or may not be a fee for a transaction to be paid, which of course will enter the decision on whether you buy at a certain price or sell at a certain price. Now, it turns out that a very nice modeling framework has been developed for such problems by Pierre-Louis Lyons and Jean-Michel Lazary actually Jean-Michel Lazary and Pierre-Louis Lyons, to be alphabetical, in the last year. And what they assume is very similar to what Eva had yesterday, that each player satisfies, well, the trajectory of each player evolves to a certain stochastic differential equation. Okay? And each player tries to find an optimal strategy. And the optimal strategy is this parameter alpha, or this function alpha I that enters into the equation, of course. And how is this optimal strategy to be found? Well, he wants to minimize a cost function L. Okay, and the cost function L basically is set up by assuming a certain Lagrangian L and by assuming certain interactions of the players. Okay, and then you take, well, you integrate over time and you take the expectation of the whole process. This would be the cost function that the player wants to minimize. Okay, now there's a mathematical process of dealing with this, and this is basically through Nash equilibration and doing a mean field limit, very similar to what we know from kinetic gas theory, meaning taking the number of assuming that the number of players is very large and taking it to infinite. Now, in the end, after complicated mathematics, what comes out is well, as typical in control, is a system of, or in stochastic control theory, is a system of Hamilton-Jacobi-Bellman equations. So what you see is you have a viscous Hamilton-Jacobi equation for an unknown function u, which is related to the optimal cost function L, and you have a transport equation for the density of players in the market. Okay? Unfortunately, what you have is a forward-backward coupling of those problems, again, as typical in stochastic control theory. So this is, from all points of view, this is mathematically a very, very challenging class of problems. Now, I mean, I don't want to go into details here. I just want to show you a problem that we have dealt with recently, which is sort of related to this to those mean field games, in the sense of that it is a mean field model for price formation, but it doesn't have the game aspect in it. And this was also formulated by Lazary and Lyons in their original paper. So what we have here is we have a market on which we have one economic good to trade. And trading is continuous in the sense of that when you sell a good, you immediately want to rebuy, and when you buy a good, you want to immediately resell it. And for certain markets, this is, of course, realistic. Think of energy or oil or something like that. Okay? So what we are interested in is to find an equation for the signed density of buyers and vendors. And what do I mean by signed density? I just mean the difference of the densities of buyers and vendors. Okay? And of course, the price at time t should also be an output quantity of the problem. Yeah? And how is the price defined? Well, the price is defined as the zero of this signed density. Okay, hopefully there's only one, let's say. Yeah? So Lazary and Lyons actually formulated a very, very simple looking one-dimensional parabolic equation for this signed density f, which you see here. So here you just have the random effect entering. And on the right-hand side, you have those delta kicks here. And there I should say something. I should say that this is a market at which you assume that there is a fixed transaction cost A. So every time, for every transaction, you pay the fee A dollars or euros or whatever you prefer. Okay? So what happens here is that basically you get kicks at, you have delta kicks at the price P of t minus A, because this takes again into account what you want to pay after you had paid already transaction fee, and the other one at x equal P of t plus A. And what then, by assumption, what you want is that f is positive to the left of P of t and negative to the right of P of t. And P of t as a free boundary is the price, is the zero level set of the solution, and that is what you can think of as the price of the transaction, of the average transaction at time t. Now, this looks extremely simple, right? I mean, this is a parabolic equation, one-dimensional. It has some kind of linear substructure, very nice linear heat equation substructure to it, although it's a nonlinear problem, of course, right? Because P of t is determined in a nonlinear way. Maybe I should say one more thing. You have a strength of the kick, and the strength of the kick is just the transaction rate. So you count basically how many transactions take place at time t. Okay, so this is what you have here. Now again, as I said, very simple looking problem. So when I saw it for the first time, I said basically, I thought you can basically walk over it and solve it almost explicitly. Okay, then you start to do your estimates, 1D heat equation. You have, of course, tons of techniques. And sort of it turns out it's not simple, it's complicated. And how do you prove the regularity of P of t? And we had big problems, and nothing worked, and many papers were written on it. Okay? And finally, let me just show you some geometry of the problem. So I mean, this is the x, t plane. Okay? So geometry is assume you have your price P of t here. Okay, then you would sort of have a parallel curve, which is P of t minus A, which is where one of the delta kicks happens. And then you have P of t plus A, where the other delta kick happens. Okay, now look at the problem, look at the solution at a fixed time t. Then it'll look like this. It'll be smooth, except in those 2 points. Well, it solves the heat equation everywhere but at those 2 points, P of t minus A and P of t plus A. And at those 2 points, what you will realize is a discontinuity in the first derivative of the solution due to the deltas, right? Now, there is a factor in front of the deltas, which is this transaction rate, right? And it turns out actually, it turns out that if you look, say, at the positive part of the solution, which is what happens to the left of the price, then this kick here this kink here is precisely the negative value of this kink here. Okay, that makes you think, right? That makes you think of something very simple. Just shift the positive part by the value a to the left and add it to the solution. Now, what will that do for you? It will just move this singularity out by another value of a. Okay, now keep doing this. Keep doing it infinitely many times. You will move out the singularity to minus infinity. Do the same on the right-hand side. You will move out the singularity to plus infinity. And what have you achieved? Well, you have transformed the problem. Oops. You have transformed the problem into the heat equation. Okay, and the nice thing about the transformation is that the price, P, will still be the zero-level set of the solution of the one-dimensional heat equation. And I have to say that this problem taught me a lot about mathematics, and that is, maybe you don't want to throw all your complicated tools immediately at the problem, but instead maybe do something that Luis Caffarelli likes a lot, and that is to look at the geometry of things. So here, basically, once you have the heat equation, you have everything that you need, and you can analyze the problem basically to the very end. Okay, just finally, just one short comment on another socio-economic problem, and that is opinion formation in human societies. There's, of course, many, many ways of modeling opinion formation in human societies, which, of course, the most simple and most most widely used way through cellular automata. But since we come from partial differential equations, we don't really like that too much, and we try to use other modeling approaches. Now, question is, of course, how does the opinion evolve in time? And the main assumption that we want to make here is that opinion formation is really determined by binary interactions between people. That is not always the case, right? I mean, there are the other processes that clearly influence opinion formation, reading of newspapers, strong leaders, media in general. So there is many mechanisms, but let's keep it simple. And here is a very simple modeling, a very simple but very effective modeling approach, mainly due to my friend Giuseppe Toscani, where the idea is basically think of the change of opinion in a human encounter as a collisional process, as in kinetic theory. So basically, assume that two people meet, they have their incoming opinions, which you call V and W, and then from those you compute outgoing opinions through the encounter. And they may be influenced, of course, I mean, they may depend on the relative difference of the opinion, there may be a random process in it, and so on. So in the end, when you sort of accumulate the process, then what you find is that the evolution of the distribution of opinions will be covered by a Boltzmann type equation, very similar to kinetic theory, where here, basically on the right-hand side, you see a very complicated, actually here not so complicated, quadratic type collision operator. And then you can sort of attack the equation through all kinds of kinetic techniques that we have developed in the last time. And actually, it turns out that we have really used this model, and we have applied it to an election process in Carinthia. Probably most of you know where and what Carinthia is. It's the southernmost province of Austria, which was sort of the homeland of a very important Austrian right-wing politician, Jörg Haider. And what we have done is we have tuned the model towards an election which happened in the year 2004, and then we have gone forward and computed and double-checked with election results in the year 2009. And it turns out that a very remarkable process had happened in between 2004 and 2009, and that is a new party was formed, of course, another right-wing party was formed in Carinthia, which sort of then took the, quite a lot of the votes. And turns out that our modeling, computations, you can really see. So I mean, this would be like the political spectrum. This would be the left end of the political spectrum. This would be the right end of the political spectrum. This would be time. And you can really see the branching process that happens, split off of the two parties. Now, of course, the next question, well, the question that you will ask is, how well did you tune the parameters to what you wanted to get? And I have to say there was some tuning, but it wasn't really all that much. So we were pretty happy with those results. Well, thank you for your attention.